Hopefully that works. Okay.
Okay, so nice to meet you all. Um, Today I'd like to give a short introduction on SAX. Let me share my screen. So I'm going to do this on um, with the help of a notebook. Um, we have I have this repository here. It's called SAX Workshop. So github.com/Laporte/SAX Workshop. You can go here, you can try to clone it and run it yourself. Um, I tried to make it runnable in Colab, but there's an issue with uh, one of the GDSFactory plugins that doesn't run. But you can try to run it in Colab. It would be nice if you kind of go along with me, at least for the beginning part. Um, or you can install it locally on your computer and run it in Jupyter Lab. That should work too. So I'm gonna start, uh, let me see. I'll just go to my workspace folder. I'll start Jupyter Lab. So let's go through the notebook. Please stop me at any point. We have time. I'm not sure if I'm gonna be able to fill the hour. So stop me, ask questions if something is not clear or if you want more information about something. For the rest, I'll just go down the notebook and try to introduce SAX this way. So if you don't know, SAX is actually a S-matrix calculator. So it calculates the S-matrix of your circuit. So from a bunch of smaller S-matrices. And the way we represent S-matrices in SAX is basically by dictionaries. So you have port combinations, in this case, in zero, out zero, couples to transmission. And then the cross terms coupled to a kappa term, like a coupling term. So it's kind of a very natural way to represent S matrices because usually you're thinking in ports of your components anyway. And also, this way of representing your S matrix is inherently sparse. So like once it gets converted into like an internal representation, this will be a very efficient way to represent your S matrix. So that's basically how that's basically the convention in SAX to represent the user-facing S matrices as dictionaries. But of course, yeah, because it's sparse, there's kind of repetition here. There's some utility functions in SAX to make that kind of less painful. For example, many of the photonic components we work with, if not all, are reciprocal. So you could use SAX as reciprocal for that. And that means that if you define a port combination in one direction, it will have the same yeah, so if you define it in one direction, for example, from here to here, then it also has the same S matrix from there to there. So that's kind of our first model. We created basically a perfect coupler. Um, that's how we do it here. That's just one S matrix though. So in many cases, you want models. Models that are, for example, wavelength dependent, but you could also add process parameters or temperature. So the most natural way to go from a single S matrix to a parametrizable S matrix is to just wrap it into a function. So that's basically what we do in SAX too. So representing your S matrix is just a function returning a dictionary mapping port combinations to an S parameter. So that's pretty straightforward. Yeah, for example, this is now a coupler, and we can vary the coupling ratio, for example. with a different coupler ratio, you should get a different value. Um, and then we can also define waveguides. This one has this is a simple waveguide model where the um, effective index changes slightly around the center wavelength. So it's just with normal group index calculations. We can use that model a bit later on. Um, yeah, so those are the first models. We can put those in a circuit. In SAX, we have this notion of a netlist, which is kind of following the netlist definition of GDSFactory. So basically, you define your netlist as a dictionary of instances, connections, and ports. So in the case of instances, you basically say, my left instance of my coupler, I call that, I use the model for the coupler for that one. For the top, I use the waveguide. For the bottom, I use a waveguide. And for the right, I use a different coupler. So that's kind of a very basic definition of an MZI. We'll get to a little bit more interesting definition of an MZI later. But this is just to show you how how you would define a circuit. So rapid and sax.circuit. As you can see, you can just use the couple. You can just use the model as is, or you can use the model with like some default settings baked in. That's kind of useful if you know that these parameters are not going to change. You can already define them at the definition of your circuit. So yeah, what you get back from this sax.circuit call is not an S-matrix. So to be clear, what you get back is basically not a function. So if you look at MZI, it's just a function which parameters, basically the instance names that you used. So we have MZI takes left, top, bottom, and right. So we have left, top, bottom, and right here. The reason that we want to have a function is that sometimes once you created a circuit, you want to play around with it, you want to optimize it, you want to do maybe Monte Carlo with it. So like you basically in many instances you're going to want to change the parameters according to some context. So for example, if we can run this, but we can also say the top waveguide length, let's make it a little bit longer. And then the S parameters change. Later, when we get to plots, it gets a little bit more interesting. But right now, for the mechanics, this is basically how you change parameters. Of course, like many parameters, if you have a look at the function definition here, are repeated, right? Like, for example, the most prominent one is wavelength. Like most components will have a wavelength parameter. It would be very annoying if you have to specify wavelength for all the components separately. So SAX also accepts top level parameters. So for example, you can say wavelength equals 1.3, and that wavelength parameter will now be distributed over all subcomponents that have wavelength as a parameter. So the coupler model was a perfect coupler that doesn't take a wavelength parameter, so that one won't accept it, but it will just ignore it. And then top and bottom will use the top level wavelength, and then yeah, and so on. So if you define at the top level, that's kind of a more convenient way of using circuits. And in 90% of the cases when running simulations with SAX, you're going to want to define your parameters on the top level in the root of the function call. So we already had a look at the signature here. So that's kind of the discussion that I did here. So yeah, basically sax.circuit is the most important function of SAX, and this function returns a function, which is a model itself, right? The MZI is just a function. It also returns an info structure. You can usually ignore this. This is not so interesting. It kind of contains it contains a dependency graph, like how are the instances related to each other. But like if you're not like debugging anything, like you probably won't need it. Um, so yeah, this is usually how you call it with like global parameters. And you can also bake in parameters in the netlist definition. But yeah, so that's kind of the mechanics of it. That was maybe a little bit dry. So let's go to like a more interesting example where we do a simple wavelength sweep of our model. So if you're not familiar with Python or with NumPy, like you might be tempted to do a wavelength sweep in a loop. Um, it's possible, like you see, like, but it takes a little bit. It's a little bit slow. And you get basically a list of S-matrices out. It's not really a very ergonomic way of doing this. Like in SAX, you have to get used to it to actually do everything vectorized. So basically, if your parameter takes a wavelength, it also takes a vector of wavelengths, right? So that's kind of for people that are used to NumPy, this will be very straightforward and yeah, to be expected. But like I sometimes repeat it because I still see people doing loops. And you can take this into the extreme. Like you can do a whole Monte Carlo simulation over 5 different parameters with just one function call if you want to, and we'll get to that a little bit later too. So and what we have when you do a vectorized call is basically every S parameter is an array of S parameters. And this doesn't need to be 1D. You can do this as many high dimensional as you can think of, as long as your internal model is supported. So let's have first look at this simulation, typical MZI transfer curve. So we'll make this a little bit more interesting now. Where SAX, so this is kind of the basics of SAX. You can define your circuits from scratch with SAX. You can define everything by hand. But in general, usually you will start from, at least very often you will start from a layout or from another tool. So in this case, for example, you can create an MZI in GDSFactory. Let's have a look. There's an MZI with a heater on top. Also still a pretty simple component, but like we have the layout here, and we can actually go from the layout and then simulate our circuit like that too. So GDSFactory has this way to get the netlist from a circuit. So we can do this here. You can have a look at how it looks. This is already a little bit less human readable. It's also pretty annoying to if you would ever want to write this yourself. So that's why like starting from GDSFactory, where you just have to define this but much code, is sometimes nicer to work with than defining everything from scratch. So this netlist can also be used by SAX, but you need to specify models for each of the subcomponents, right? So we have a 2x2 here, we have a bend, we have a straight, we have a heater. If you're unsure what models there are in your circuit, you can always use SAX.get required circuit models to get a list of models out from your netlist. And then it tells you basically, you need to specify a model for the bent Euler, for the straight, for the heater, and for the MMI, in this case, the 2x2 MMI. So we can do this. Let's define models for those. So as you can see, like here, earlier we defined some very simple models, but like in practice, you're going to want to use some more interesting models. Let's start with the waveguide model. That's arguably the most important model of your circuit. So let's let's make a effective index model for this waveguide. And because we're going to use this later in this tutorial for a basic Monte Carlo simulation, we're also going to include the waveguide width. So we can do a sweep over different waveguide architectures or waveguide structures. And then, yeah, for example, this is just a simple silicon waveguide, half a micron wide and 220 high, 220 nanometers high. But like we varied the width from 400 nanometers to 600 nanometers. So we'll have an effective index model that covers wavelength and width, waveguide width. You could add height to it too. You could add temperature. All of these things are relevant parameters that could be interesting for Monte Carlo simulations. For now, let's just focus on wavelength and waveguide width. We can fit a very simple model to it. This is a tutorial, so I don't care if this is a good fit or not. But like in general, like if your fit looks like this for an effective index model, I would resimulate it with more with a finer mesh and maybe more nonlinear fit because yeah, there's pretty big variation here. But for the model for this tutorial, this suffices. So let's go for a linear fit on our effective index. We can do the same with our group index. Also a linear fit. So this is basically a fit on the width, right? So we have already the group index extracted from the mode simulation, which GDSFactory so conveniently provides some tools to easily get the effective index of your waveguides. So we have the effective index and the group index from here, but we only simulated it at the center wavelength of 1550 nanometers, right? But using the group index, we'll be able to extrapolate the effective index. And then using this model of the effective index versus width, we'll be able to extrapolate over width as well. So we'll be able to extrapolate at least linearly over this range. We can, so for example, this is calculating the effective index at the center wavelength, which, as you recall, is 1550. So the effective index at the center wavelength for a certain width, right? So these are simple models. Usually you'll want a little bit more better models. And then this is then the effective index for a certain wavelength and a width. So like given the effective index at the center wavelength, we can extrapolate with the group index to the effective index of our yeah, at a certain point. So we can plot this model, looks like this, and you can see we have varying, yeah, the effective index get bigger for wider waveguides. And now we have a better model of a straight, or at least a model that takes more parameters, that takes wavelength, width, length, and loss. Loss is still just a value that you have to supply, but like you could probably just use the imaginary index returned from this mode calculation to estimate the loss. I didn't do that this time. So we have our straight model. For the bent model, you could do the same here. I'm pretty sure if you look at this modes calculation that it takes a bent radius. Yeah, it takes a bent radius. So you could specify bent radius, and then you get a whole set of new effective indices, group indices, and so on out. For now, and for this tutorial, I'll just say they're the same as a straight, and I just add a little bit extra fixed loss. I'll leave it as an exercise to you guys how to make it. I mean, you can just copy basically what we did for the straight, but add a bent radius. A heater, often heaters are characterized by the power needed to shift by a phase shift of pi. So I just pulled something out of my hat here. I say the power to for a pi phase shift is 50, whatever the units are. And then the input power, initial input power is zero. So that will basically, at this case, it will make sure that like it will be the same as a normal straight. And as soon as you apply a little bit of power, there will be some extra phase shift. MMI, yeah, I also pulled something out of my hat here for this model, but like the usually have like two curves. Sometimes they're a little bit shifted from each other, but generally speaking, like it's kind of a, a Gaussian-ish response. Um, yeah, so now we're ready to simulate this circuit because, as you recall, we had to specify four models: the Euler band, the straight, the heater, and the MMI. So let's go on and do that. So let's have a look at our circuit one more time. I don't know why my screen is always jumping. Yeah, and then get the netlist. These are the models that we needed. And then we simulate them. This time we specify. So this is basically how you do this. And I already implicitly did this here above too, right? Um, you specify a netlist and you specify the models that you use. So we do the same here with our newly made models in our sax.circuit call. Where is it here? Yeah, so we define the models and we already have the netlist, so we can create our slightly more realistic MZI and do a plot. So yeah, this transfer curve, yeah, you see there's a little bit more loss, a little bit more, yeah, envelope due to the MMIs. So this looks a bit more realistic already. Yeah, the nice thing about using SAX is that like it's based on JAX. So JAX is a machine learning library initially developed at Google. So because it's machine learning, there's a lot of cool machine learning optimization techniques that you can use. Especially also you can do gradient-based optimizations. So that's an extra dimension that you can add to your optimization portfolio to optimize this MZI. So like I'll quickly show how this works. I have to give a side note though that gradient-based optimizations for photonic circuits are not always the best approach, but like I think it's cool that you can do it. So usually you begin with defining a loss function. And in this case, if we dissect this loss function a bit, we say it takes the power as input. So that's the heater power basically. So you're basically asking like which power do I have to give to minimize the O1 to O3 connection, which should be the through connection, right? Because ports are O1, O2, O3, O4. So like O1 to O3 would be through and O1 to O4 would be cross. So I annotated it wrong. So this is the through connection of the MZI that you're trying to minimize basically. And we minimize it at a certain wavelength. So that's 1.54. So that's at this line. So basically what we want is that this trough moves all the way over here to get a minimum here, right? The through should move here. This is kind of a magic function from a JAX. It's called JAX.grad. It calculates the gradients for your loss function without basically you having to specify them. So That's kind of nice because with these gradients you can do optimization. Or it actually returns a function that calculates gradients depending on the inputs. Can use the atom optimizer, which is a very well-respected optimizer. And basically every step we're gonna do this step function. So this is kind of internals from JAX. I'm not going to go too deep into it, but basically you start with an initialization function, an update function, and a params function. And then the initialization function gives you some kind of state that you pass around. And then the params function, you can retrieve the parameter, and then the update function just updates the state given the gradients and so on. That's kind of a very functional programming approach to doing gradient descent here. If you look at other machine learning libraries like PyTorch, their approach is a little bit different, sometimes a bit easier to understand. But like once you get used to this, like you start to like it as well. So let's do an optimization. Oh, it's going higher. Okay, now it's starting to move down. Okay, so our best loss was low. We found a power that minimizes that loss, and let's see what it gives. Yeah, here you see we found the minimum of our a minimum of our MZI for a certain power. But like this is kind of an easy problem to minimize. Like you don't have to use this gradient-based approach. I just show it because I don't think there's many more simulators that actually can enable this for you. But like an alternative approach would just to be using SciPy dot minimize basically, and that will give you the same results. So we start from 0 and get a certain minimization result. Yeah, so that kind of brings us to a Monte Carlo. We've done already a few simulations. They're always for a range of wavelengths, but like no other parameters are varied. So I wanted to show you that like you can quite easily do Monte Carlo with this. And actually, it's just this one-liner that is the Monte Carlo simulation, basically. So we simulate. And as you can see, we simulated for, let's see, simulated for 100 widths and 100 wavelengths. The wavelengths are on the x-axis. I didn't annotate it here, but wavelengths are on the x-axis, and then the widths are just all the different curves that are plotted on top of each other. And as you can see, this was pretty fast, right? Like it was not even 2 seconds to do basically 10,000 data points. You could do it even faster if you JIT the circuit. I won't go into that right now, but and basically this is the magic line where you do all these simulations at once. So you don't use any loops. You just basically use standard NumPy broadcasting rules, basically. And if you're not really familiar with broadcasting in Python, I can give you a quick demo because it's pretty powerful, and it allows you basically to almost, in like many cases, you will be able to avoid loops altogether if you understand broadcasting in Python. So basically, broadcasting is as this. Like the first thing you have to understand is like what are these indices with nonce, right? In our case, wavelengths is 1D, but if I index with none, it becomes a 2D array. So basically, 100 by 1. If I put the none in a different place, then you basically get a dimension of size 1 here. So that's basically what indexing with none does. At every place where you put a none, you get a dimension with size 1. And now broadcasting means that like if I have, I can do this for the wavelengths, but I cannot do the same for the widths. So let's do widths. Uh, so we have a 1 by 100. I think I wrote it different in the code, right? So let's do it like this. We have a 100 by 1 wavelength array, and we have a 1 by 100 width array. Now, if we would add these two arrays together, you might think, this is never going to work because they don't have the same shape. But because broadcasting basically means that like it still will work, and the result will be an array of, in this case, 100 by 100. So basically, what you do with broadcasting is, if there's a dimension with size 1, then it will basically use that one for every element where the dimension is not 1 in the other array, basically. So you can add them together. In this case, we can simulate them together and they will still broadcast together. And that allows us to basically go from a 1D width of size 100 and a 1D wavelength of size 100 to basically a 2D S matrix. I mean, 2D S parameter actually, right? In 0, no, it's 01 or 3. So each parameter is 100 by 100 for each basically wavelength and width combination. So that's kind of the way to do this in JAX and in SAX to make it as efficient as possible. Like if you would want, basically, let's say you have waveguide height. We didn't define this now, but we could do something like this, right? We do none, make it like this. And that would broadcast in 3 dimensions. And this way you can basically add as many dimensions as you want, and and it will stay very efficient in SAX. So that's basically the broadcasting rules. I won't go over it here because I explained it above. And that brings us to, I mean, so far the circuits have been pretty simple. We can also define hierarchical circuits in GDSFactory or in SAX, doesn't matter. So we can basically put two of those MZIs that we created earlier and route a simple waveguide in between. And then here it's important that you call on this circuit, because it's a hierarchical circuit, you have to give the recursive equals true flag, which will ensure that like you'll get all the relevant netlist spec. But for the rest, SAX will just take it and work with it. It doesn't matter. So you can simulate this as well without even having to think about what the netlist was, which is pretty great. Yeah, and I think that's kind of it for today. I think there's a few things that I haven't covered, like multimode simulations, alternative backends, like internally, like all the simulations that I've done have used our default backend, which is KLU. But there's other backends, like an additive backend, which basically instead of doing multiplications for every S-matrix connection, basically adds stuff together, which is useful for path length matching and stuff. You can do jitting. I think I've done it a few times implicitly without going too much in detail about it. But like as soon as you're gonna run your circuit more than once, it's probably worth it to jit it if your models allow it. And yeah, I mean, there's also some nice examples in the SAX repo. Like for example, the 7th example notebook in the SAX repo goes onto a more in-depth Monte Carlo simulation, where you basically create a wafer map and basically do a layout-aware Monte Carlo simulation. So all of these things are possible. But yeah, I think for now, I think I'll end it here. I will take any questions if there are any, and yeah, let me know uh, if there's anything you would like help with SAX. I'm happy to help.
Yes. One quick question. How do you make sure that the S matrix is say like unitary, or like how do you enforce these physical constraints?
Yeah, so usually we write tooling around that. It's not that SAX explicitly enforces this because some S matrices, I mean, like SAX just will calculate it with whatever you can do. But there's some tooling inside SAX to check if it's unitary or to check if or to make it unitary. It's kind of deeply buried, but maybe I should expose them more. But I'm not checking anything before doing the simulation. I think I gave the freedom to the user to do that or to not do it if they don't want to do it. But yeah, that's important, of course. You want your circuits to be unitary or at least passive in most cases.
So may I ask a question?
Sure.
So is there any flexibility in choosing different range of parameters or maybe exploring the different kinds of uh, geometric designs of waveguides or metamaterials to perform simulations in them? Like if we make use of SAX specifically.
Yeah, I mean, SAX is as flexible as it can be, right? Like you just give the parameters you want. For like here, like we can increase the parameter ranges and like it will just simulate it. Um, for the second part of your question, what was that again?
So basically, if you want to simulate metamaterials or
Yeah.
nanostructures, for example, let's consider a uh, plasmonic array on some other semiconductor, and we want to simulate that. We just do the forward design or the forward
Mhm.
simulation of that
Yeah.
geometry. Is that possible to do using SAX?
If you can express it in S matrices, then I would say it's possible. If you can't, then you probably need
Okay.
another tool for it. Yeah.
Has SAX proven to improve simulation time compared to other methods?
Yeah, I mean, we have been using it at Rockley and compared it to, for example, Optim, and it's at least an order of magnitude faster for the models that we had. Also, it gives you a lot of flexibility. Like uh, we were used to using a lot of or having a lot of higher order modes in our wide waveguides in at Rockley. So we needed to take all of these into account, whereas most tools they only consider basically TE, and if you're lucky, they consider TE and TM in the cross terms. But for our purposes, that was not enough. So SAX gave you that option too. I didn't go into that detail today, but yeah, you can have a look into that too. So yeah, it is very efficient. It's backed by a sparse matrix solver called KLU, which I think is a go-to standard by now for doing circuit-related problems, and which makes it basically very fast.
Okay, thanks. Another question I have is there any flexibility in choosing the gradient descent methods? Like for
Yeah,
example, a joint gradient descent or some other kind of
yeah.
gradient descent.
You have complete flexibility. Like if you want to use a certain obscure optimizer, you can use that. If you want to basically do it yourself, you can do it too. You get access to the gradients yourself, right? So like you can optimize it yourself. But like most of the time, you're gonna want to use an optimizer. So like we have here Atom, but we have RMS prop or stuff. But these are basically from the Jackson's example libraries. But like for any uh, any thing, you can always have for any kind of optimization problem with JAX, you can use any optimization library that you want, or any machine learning library that uses JAX under hood will be able to optimize your circuits too. So like you have complete freedom there. I found that like
Okay.
Adam is easy for these. It's good enough for most problems, but like if you want to go to special versions, you can do that too.
Okay. Thanks.
But yeah, like I said, you have the gradients, right? So like this is the gradient on your loss depending on the input. So like if you do rat function of 13, that's basically exactly the gradient um, the parameter that you on the parameters that you're optimizing. So you can do with it whatever you want. Like I use this grad function as well sometimes to get the group index. Like let's say I have a model for my effective index, then I can just use the grad function to get the group index of my circuit of my waveguides. Like there's no need to like create a second model for it or fit a second model to the group index. You can just use grad for it. Yeah, stuff like this.
All right.
Can you elaborate a bit more on the Monte Carlo simulations with wafer maps? What exactly do you mean by that?
I can actually show you. Let's see. I have. Uh, go through here. Did I run it? Yeah. So in this notebook, this is just in the public SAX repo, and then go into the examples folder. But like we do a similar approach. We have an effective index versus certain parameters. We simulate an MZI optimization, so that's kind of what we did. But like with layout aware, I mean, like sometimes on some wafers, like the waveguides are a bit thicker or a little bit like near the center or near the edges. Like I won't usually it won't be looking like this, but like usually like you have a kind of you could make a map over your wafer where certain features of your waveguides will be different than others. And usually you generate like 100 maps or so with certain correlation lengths for these features. And then you can use that to heuristically find like a MZI that works better in general. Like for example, starting from a certain MZI, where did we define it here? Let's say we define an MZI like this, right? You have a branch or an arm that goes up and an arm that goes down. If you put this over like 100 wafer maps that are auto-generated with certain correlation lengths for waveguide width, for example, you get a certain variation, right? But then if you decide to put your arms closer together, then for example, the effective index differences that these both arms experience will be smaller because they're closer together. And then you can see that like this MZI performs better over many different wafers. Like this is kind of cool to show that like you could do something like this. But of course, how do you get these wafer maps, right? In general, many fabs only give like global variations from wafer to wafer or from lot to lot and stuff like that. But they won't say like what the correlation length is within a die or within a wafer itself. So yeah, I think so far this has proven to be somewhat of a toy problem. I mean, we haven't really been able to apply it in practice because of lack of knowledge on how these features behave. But you could you could put a lot of time and effort in making these kind of characterizations, and then you could, in principle, do these kind of layout aware Monte Carlo simulations.
Very cool. Actually, on that note, what's so different about multi-mode simulations, other than, there are multiple modes to take care of?
Yeah, so like as it's not necessarily that much different, but the like you could basically create a component with like 10 ports, and each of these ports have different names, and like do it like that. But SAX makes it just kind of slightly easier for you to define them and to work with them. The Well, there's of course things that you have to take into account, like cross mode connections and stuff, and these kind of things. But like in general, like it was just a few lines of code to enable multimode for uh, yeah, to enable multimode in SAX. But that being said, it was still annoying that like commercial tools wouldn't offer it in general. Like you could define a component with more ports, but that's not really ergonomic after a while, because you have to connect all these ports separately then, and you might make mistakes.
Yeah, that's fair. And then on the waveguide models that you typically use, how do you incorporate the effect of sidewall roughness? Is it something you phenomenologically include, or is there
Yeah. So
something
far
else?
on most models that I've used for like production simulations, let's say, then sidewall roughness is basically a parameter you would get from the fab, which kind of change, it's kind of a multiplier, like a loss multiplier, maybe some phase uncertainty, stuff like that. But like in general, like we just modify or tweak our model a little bit to add extra loss from it, or um, but yeah, so far like I haven't really modeled it myself. Um, yeah.
Cool. And then you mentioned everything is using a source solver under the hood. So
Mhm.
to my understanding, there are two main ways to solve these linear systems, direct solver or iterative method. So you're using direct solvers for all of them?
Yeah. Yes, I do. Like you can have a look in the SAX repo as well, the internals and the backends. What we have here is so we have an iterative solver for circuits, but it's a lot slower than like the direct approach. And here I explain like basically the mathematics on how we're doing this. But this is basically the final result. So we have the S matrix is some kind of part of your connection matrix with the block diagonal S matrix, and then you solve here with KLU for this internal one. Um, yeah, and all the code is open, so you can have a look on how it's implemented. But um, that's kind of how we're doing it.
Right. If there are no more questions, I think our hour's almost up. So, is there anything last minute anyone wants to add? If not, thank you so much for giving this workshop today. I think everyone really appreciates it.
Yeah, no worries.
Appreciate you taking the hour of your time. I think I might have gotten the time zone difference wrong, so I'm sorry about that, but I appreciate you coming anyway.
Yeah, no worries. I made it. Okay.